So this is a sapling question. And the reason I like it is just, you don't need to know this chemistry yet, but it's good to just practice thinking about moving arrows and when and how we move electrons and all those kind of things, right? So the first thing is arrows always start at electron density, right? We always move arrows towards the more electronegative, right, things usually. So if you look at this, what happened here, what bonds were broken, right? So we'll do exactly the same thing we do with a mechanism, right? What bonds are broken, what bonds are made. So what bonds are broken? Bonds broken. Was what? There's only one bond broken. So C to Cl, sigma bond, right? And usually also talk about like numbering, a good numbering system, right? Numbering system, 1, 2, 3, 4, 5, 6. Right? So it's one of those cases where you got to get used to, you don't need to know why this happened, you just know what happened. Draw the arrows to make sure this makes sense. Right? So I'm presuming that's number 1, 2, 3, 4, 5, 6. The reason I thought it was number 1 because, right, the chlorine left carbon number 1. I'm guessing something happened to carbon 1. There'd be a carbocation there, right? So I broke a carbon chlorine sigma bond, C1 actually, right? It's actually C1 to Cl sigma bond. So how am I going to draw arrows to represent that? So I guess bonds broken, but what else happened? What did chlorine get over here? What did chlorine end up with?
The electrons.
How many?
2 of them.
Right? So another thing to think, it's not really a bond being formed, but you could also say, not but, you could say Cl got 2 electrons as well, right? Oops, that looked bad. Don't do that. Negative charge. Right? Chlorine got 2 electrons as well. Right? So you got to draw arrows showing it getting 2 electrons. Right? So the arrows you'd want to draw, I draw the electrons in the bond, right? How many electrons in a bond? 2. Just show those 2 electrons going to that chlorine. Right? Last one going to that chlorine. And that's all they're looking for here.
Do you even have to put the HF on carbon 1?
No, they didn't. They just showed it there just to show that it was still there, right? Because this H is still here, right? We just don't draw it in.
Yep.
Right. So we'll work on more of these, just analyzing. Right. Tomorrow we'll look at is you'll get products, you get start materials, you analyze what bonds are formed, what bonds are broken, number the carbons, and you work on identifying electrophiles and nucleophiles every step of the way. So this one's really not this is not an electrophile nucleophile type thing. It's just chlorine just taking the electrons essentially.
There's like 3,3-dimethyl-1-butene and then plus hydrochloric acid.
So let's say 3,3-dimethyl-1-butene. So butene, 1-butene, 1, 2, 3, 3-dimethyl, right? Dimethylbutene, right? Plus HCl. Okay. So this is kind of taking what we learned another step further. Right? So every step of the way, so you don't know the reaction products here. But I'm going to take it a step further. I'm going to show you the reaction products. Say I gave you the products. The product for this reaction is going to be this. That is the product of the reaction, for emphasis. That's the product of the reaction. So take some time and we'll look through this. Think about what bonds need to be formed, what bonds need to be broken, a numbering system, and let's get that started. Okay, we're back. Let's analyze this. First thing, let's say bonds that need to be broken. But let's do how about we do, usually the first thing I should do is a numbering system. Let's number some of these carbons. So I'm just going to start from right, just because that's maybe easier. 1, 2, 3, 4, and let's call these guys 5 and 6. Is that okay? All right, you all agree? Good. So this is where it's hard, right? But if we gave you the numbers, you might be able to figure this out too. But this is where it gets a little difficult. But 1 and 2 are here. 3 and 4. And let's call this one 6, and that is 5. All right. So, what bonds do we need to break? Right? So we need to break the pi bond between which two carbons?
1 and 2.
C1 and C2. Good. What other bonds do we need to break? The sigma bond between H and Cl. Good.
And then the 3 pi
The sigma bond between C3 and C5. Is that it? I think so. How about the made ones? Bonds made, what do we need to make?
Carbon, hydrogen, sigma bond.
A sigma bond between which carbon and hydrogen?
Going to be carbon 2 and hydrogen from the.
It's not carbon, I think carbon 1 got a knot. Did carbon 2 get a hydrogen? How many hydrogens does this carbon 2 have right now?
It's got 1.
1. How many does it have here?
It's got 1.
So did carbon 2 get a new hydrogen?
Yep.
Which carbon did? C1 get a new hydrogen. What other bonds do we make? C3Cl sigma. And what other bond do we make? Sigma C2C5. Alright? First two steps in any mechanisms we do. Get a good numbering system. What bonds are made, what bonds are broken. Right? The bonds made, bonds broken lets you know when you're done or when you're not done, right? It's like a little checklist. You know what you need to do. Okay. So the first step, in the next, so we did numbering system, we did bonds made, bonds broken. And the other thing I always asked you guys to do was identify the electrophile and the nucleophile in each step. Right? So which one of these, as long as you can identify one, the other thing has to be that, the opposite. So what's the easiest one to identify here? As an electrophile or nucleophile? What's the easy one? The electrophile. What is the electrophile? HCl, right? Because HCl is the same as H+, right? So it's super electrophilic. So that means the nucleophile has to be what? But it's not the alkene. What part of the alkene? The pi bond. You gotta be specific, right? Because the alkene is a pi bond and a sigma bond. That's right. Be very specific about which part is the nucleophile. So it attacks the H. Chlorine gets the electrons. New H is on carbon 1, like we said. So that's 1, 2, 3, 4, 6, and 5. We also made Cl minus, right? So the other rule, identify electrophiles, nucleophiles each step. What's the other rule? Balance your charges. So we have a Cl minus, we better have a plus charge somewhere. Where's the plus charge going to be? On carbon 2. Good. So this, you guys know this. At this point, you know this, right? You knew, right? You knew. Why did you choose to have the plus charge be at carbon 2 and not carbon 1? We already knew that, but if you didn't know the product, why would you pick the plus charge at 2 versus 1? It's more stable. Why is it more stable? That's a fact. Why is a secondary carbocation more stable than a primary carbocation? More hyperconjugation, right? So this is a secondary. It's more stable. It's more stable because it has more hyperconjugation interactions. But is the secondary the best? No. What's better? Tertiary. So if we could make a tertiary one, we would. So here's the crazy thing about carbocations. They rearrange. Right? Things will start moving around, right, to make up something more stable, right? Carbocations are really high in energy. So if we can make them less high in energy by rearranging them, we will. And we know a tertiary carbocation is is more stable than a secondary. So what do we have to do here? I'm going to take these 2 electrons here, and that whole carbon is going to jump ship with its 2 electrons. Carbon 5 is going to carbon 2. Right? It's a methyl shift. It's a 1-2 shift. Alright, it's going from carbon 1 to carbon 2. 1, 2. A 1-2 shift. So that checked off our list. We'll go back and look at our list. So all of a sudden that's there. This is 1, 2, 3, 4. This is 6. This is 5. Cl minus is still along for the ride. Where's our plus charge at now? Which carbon has a plus charge?
3.
Carbon 3 does. Good. You see that? It just shifted. So methyls will do this. Hydrogens will do this. If it means you get a more stable carbocation, it'll do it. You'll never go sideways though. You never go sideways. So if this just would have formed a secondary carbocation, we wouldn't have shifted. We only want to go downhill. Right? We only do this for tertiary. We only do this for a better, more stable carbocation. Right? So the last step, what's my electrophile? What's my nucleophile here? My nucleophile is the chlorine, and that attacks the carbocation, which is the electrophile. And that gets us to our final product. So let's go back through our checklist. Do we break the bonds we needed to break? First step, we broke the C1, C2 pi bond. Good. First step, we also broke the HCl bond. Over here, right, we broke the C3, C5 bond, right? We did that shift. Right, you can even think about this part as a nucleophile, this part's an electrophile here. Nucleophile, electrophile again. Did that. In our first step, did we make the CH bond? We sure did. Do we make the C2, C5 bond? We did there. And the final step, we made the C3, Cl bond.
So this whole part is the transitional state when all this is being made.
So let's be careful. So now I'm going to make a free energy diagram for this. All right, let's label these. So let's call these are the starting materials. Right? We'll call this A, this B, and this the product. Now, A and B are what? Are they transition states or intermediates?
I guess intermediate.
They're intermediates. Why? How do you know they're intermediates? Because what do intermediates? What's the difference between an intermediate and a transition state? Intermediates have fully formed bonds. Yep, they have fully formed bonds. Right? Even though it's a carbocation, it still has fully formed bonds. It doesn't have all the bonds it wants, but it has fully formed bonds. Right? So these are the valleys in our free energy diagram. Transition states are the hills. Right? So we can't draw, or really can't, none of these are transition states. So let's draw what a free energy diagram might look like. I'll make a little space right here for it. It's not need too much. So E. So let's start off with our starting materials. And we'll start off with our products. I'm not sure, right, which one's really more stable than the other. It's not a big deal. Which one's more stable, A or E, as far as energy? Which one's higher in energy? Intermediate A or intermediate B? Which one's higher in energy, A or B? Which one's going to be higher in energy?
B is, right, because it's more stable?
B would be higher in energy, or if it's more stable, it would be lower in energy.
More stable.
So which one's going to be higher up?
A.
A, right? The secondary carbocation should be higher in energy than the tertiary, right? Tertiary is more stable. So if I put in A would be here, and B would be here, right? Because we're only going to rearrange, we're only going to do that methyl shift, right? We're only going to do this methyl shift, right? If we can form a more stable product, or more stable intermediate in this case. So our arrows would look like this. Really high one, right? Because is it hard to form a carbocation? Yeah, right? It's a high lot of energy to form a carbocation. Another one down, and another one down. So how many steps is this reaction? How many different individual steps does it have? 3. 3 steps, right? 1 arrow, 2 arrows, 3 arrows.
A is highest because it's most unstable.
Right. A is highest in energy, right? This is energy. Right? A is a secondary carbocation, which is higher in energy than a tertiary carbocation, which B is.
How did you choose whether the starting materials and the product?
That doesn't matter. I just made that up. Yep, doesn't matter. Don't worry about the relationship between these two right now. Yep, don't worry about that. Let's worry about this.
Are we gonna have to calculate it for our?
You could, if I gave you the numbers, but.
Why did you call it a 1-2 shift?
Called the 1-2 shift, right? It's a good question. 1-2 shift is because it's going from one carbon here to 2. The relationships are right adjacent to each other. 1-2
gotcha.
shift.
Okay.
That's why it's called a 1-2 shift. That's not that important, but you say it's a shift. Good.
In sapling, when it says like choose the electrophilic, blah, 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 it doesn't have to be like one of the carbons, it can be the bond.
Yes, yes. So this point is coming up is good that, so an electrophile and a nucleophile doesn't necessarily mean the whole molecule is an electrophile or nucleophile. Oftentimes it'll mean maybe one element is an electrophile, like right here. This H is the electrophilic part, right? This pi bond is the nucleophile, right? So usually it's a bond or one element or a lone pair is like the nucleophile, but you wouldn't want to say this whole molecule isn't nucleophilic, right? These carbons over here are not nucleophiles. Just this pi bond is a nucleophile. So a molecule within itself could have a nucleophile part and an electrophile part, right? A couple different parts, right? But you're always looking for the specific portion, the element, the pi bond, the lone pair, things like that are actually the nucleophile or electrophile. Good distinction.
So you basically just look for, like, when you have like an alcohol, you just basically look at the H and that's gonna be it.
Right, and so that's it comes back to what we taught you over and over again at the beginning, right? We kept asking you guys to find the most polar covalent bonds, right? Or like where the electron density was at. That's kind of what we were getting
H
at.
is like the worst case scenario.
Right. Yeah. So for this one, it's the sapling question. I think it's 27. Shows us these two molecules, a ketone and an alkyl halide. And it asks us to identify the electrophilic site in each of the following molecules by selecting the electrophilic atom. This comes back to what I was just saying, basically, right, this whole molecule is not an electrophile. This whole molecule is not an electrophile. There's a specific site that's the most delta plus, right? So where is it most delta plus? So in this molecule, where do you think it's most delta plus? Which carbon? The carbon double bond to the oxygen, that's where it's going to be most delta plus. That's the electrophilic site.
So because it says electrophilic atom, that's when you know it couldn't be a proton.
Right, but pi bonds are electron dense, so they're never going to be an electrophile.
Or, yeah.
Right, and so what about this other one, the carbon with the alkyl bromide? Where's that going to be most delta plus at? The one attached to the bromine, right? So that's your electrophile there.
The one right next to it is nothing, right?
And one right next to it is nothing, right? Nothing. Well, not nothing actually, but nothing. Right, they're not polar bonds, right?
So if we switched it around and said nucleophilic atom,
So let me just switch it around. So what if I said, if I drew, if I drew the same ketone, and I said, where is it nucleophilic at? Where is that ketone nucleophilic at? Where is it electron dense at? What part of the oxygen? Lone pairs. Right? The lone pairs here are nucleophilic. Whereas this carbon is electrophilic. Right? So within one molecule, you can have a part that's nucleophilic and a part that's electrophilic.
so it wouldn't be the oxygen that's nucleophilic, it would be the
Lone pair is on the oxygen. Yes. Right? One thing people do get mixed up with, they want to make bromines and halogens. Right? They're usually not very good. If they have a bond, they're not going to be nucleophiles. Right? Because how many bonds does bromine want to have? One. And bromine, fluorine, chlorine, and iodine, they're already on the far right side of the periodic table. They don't want to bond more than once. So if they're bonded, they're not very good. They're not going to be nucleophiles. If it's Br minus or Cl minus, that's different, right? But something like this this part will never be a nucleophile, right? The halogens hold their lone pairs much tighter than an oxygen or nitrogen would. Right? This will never be a nucleophile. No. People will try. No. Not a nucleophile. Not now, not ever. If it's Br minus, it's a nucleophile. But if bromine's bonded, not a nucleophile. So not every molecule has to have a nucleophile part and electrophilic part.
Is that the polarization?
Yeah, this bond's polar. It's a polar bond. But just because you have a polar bond doesn't mean you have a nucleophilic part and electrophilic part.
No, I mean, it can distribute itself better.
Right. So yeah, this is just like we talked about before. This bond is weak. That makes this more delta plus. This is electronegative. Right. All those things.
But it's not a nucleophile because it can distribute the electron.
It's not a nucleophile because it's a halogen and it's really happy with Ari's full octet. And yes, it could distribute its charge. But you'll never see a bonded bromine, chlorine, or iodine acting like a nucleophile. If it's bonded, no nucleophile. So this is number 30 in sapling. So this is a good way to practice kind of what I've been talking about, how we analyze reactions without really having to know the chemistry necessarily. What's all going on here. So again, right, let's take some time, number our carbons, analyze which bonds are formed, which bonds are broken, right? And we'll start again. Okay, so the first thing we do is a numbering system. Let's do a numbering system. So I'm just going to say 1, 2, I'm going to throw oxygen in there, 3, 4, 5. The product is 1, 2, 3, 4, 5. Right? So the one question they ask you, and we're going to take this a little step further, but the question they ask you here is, okay, this is what happens. Essentially, what's the nucleophile, what's the electrophile? So you have to choose between the alcohol and the alkyl bromide. One has to be the electrophile, one has to be the nucleophile. And you know what the products are. So which one do you think is going to be the nucleophile or electrophile? Which one do you have a hankering for one or the other? What? The O, not the O, but the lone pairs haven't drawn on the O, right? That's the element, that's the nucleophile. The O is, all right? It's not necessarily that's the most electron-rich spot, right? Here's a point of confusion. For sure, the bromine has the most electrons, right? But is the bromine willing to give up those electrons? Absolutely not, right? What about the carbon bond to bromine? Is that going to be pretty delta plus? Yep. So the nucleophile is actually the oxygen, and that's going to attack carbon 4. And as it attacks carbon 4, the carbon-bromine bond breaks. Well, carbon 4 is delta plus. That bond's polar. Let's just go ahead and break that bond. So carbon 4 to bromine, that bond breaks as the oxygen attacks carbon 4.
That's fine. So
Right.
the oxygen, the hydrogen.
Yep, so we'll get there in one step. Yep, we got to get rid of that in a second. All right, so let's just take a step back again then. Bonds broke. Which bonds do we need to break?
The sigma OH3,
The sigma,
the 3 oxygen to hydrogen.
Oh.
so O3 to H, that bond needs a break. What else needs a break? Sigma what?
Sigma
Sigma
4
carbon.
C4 to bromine. Anything else need a break? What needs to form? The sigma O3 to C4. Good. What else?
HBr.
Sigma H to Br. Right? So the first step we just checked off, oxygen is now bonded to C4. Right? So let's draw the product of these arrows. So who got electrons in this whole deal? Who ended up with the electrons? The bromine did. So the bromine has the negative charge, right? Who gave up the electrons? So who has the plus charge? Oxygen does. Right? Put our numbering back in. 1, 2, 3, 4, 5.
How
Right.
do you choose our victim? Like, why do you choose for to be hit by the electron?
Where is the most delta plus carbon at?
Never mind.
There it is. Right? The carbon bond to bromine is going to be the most delta plus, right? Because bromine is really electronegative. So what's our last step? What's my nucleophile? What's my electrophile in this last step? We need to break that OH bond, right? Oh, I broke this bond already. My bad. So how are we going to do that? The bromine's going to attack the H. And then those two electrons are going to go to the O, between the O and the H. And that gets us to our product. Right? We've broke our OH bond, we've made the HBr bond. Yeah?
When I was doing mine, I just said that the oxygen took the electrons from that bond, so it made the hydrogen plus, and then.
So you just made an H plus.
Yeah.
That's fine too. Yep, you could have said, so I think you're saying, instead of having the Br come in here, you just had the H plus, just these two electrons just go there and you made H plus.
Yeah. I did, yeah. Like,
And then you had, yep, that's fine.
So if you didn't have that intermediate step that has the 1, 2, 3, 4, 5, and then connected to the hydrogen,
Yep.
and you went straight from and broke the bond,
There?
that's incorrect.
That's incorrect, right? Because that bond is really not the nucleophile, right? The lone pair is really the nucleophile. That's what really attacks. Right? It can't be the electrons in this bond, really. All right, so this is a reaction you haven't learned yet, but
Is that the?
you can identify electrophiles and nucleophiles. I mean, you can see how it's starting to easy. It's not easy, but it starts to become very logical. If you can do a good numbering system and you can think about which bonds you need to make, right, and identify nucleophiles and electrophiles at each step, and always balance your charges.
This is a substitution.
This is a substitution, yeah. But really, only thing Sapling was asking you was between these two molecules, which part is nucleophilic? That's the oxygen. Which part is the electrophile? That part, that carbon. Yeah. Yes. Right. Again, here's the point of confusion. Right. Again, yes, bromine has a lot of electrons, but does it have a lot of electrons it wants to share? No. Right. Either does fluorine or chlorine or iodine. That's the problem. Right. When bromine's bound like this, it has lone pairs for sure. It has a lot of electrons, but does it have a lot of electrons it wants to share? No. Oxygen. Right. Not like oxygen's super psyched about this, but it's better than bromine would be. Okay, so the one time we'll ask you to do some calculations. CH4 plus 2O2. See, Hannah. CO2 plus 2H2O. So I think what you need to do is draw these out as structures. Right? So CH4, good old methane. O2, right? CO2, and then water and water. They want you to calculate the delta H, right? The enthalpy for the following reaction using the bond association energies. So basically, you take essentially the bonds you're going to break and the bonds you're going to form that are changing. They need to subtract from each other. The bonds broken minus bonds formed. So you see you have 4 CH bonds here. So each CH bond was worth 411. And you got 4 of them. So that's some number. Somebody find out. The OO double bond is worth 498. Right? And you add these things together and that gets you a number. You're welcome. On the other side of the arrow, you got C double bond to O, and you got 2 of those, and that is 799. You take that times 2, and then you have HO bonds. And you got 4 of those, but HO bonds are 459, and you got 4 of them. So you add these 2 numbers together, just like you added these 2 numbers together. And then you took, what's this number? Got it?
Yeah, for the 799 one?
Either one, the first one.
Individual numbers. So for the C to H bond, the 411 times 4 is 1644.
Yep.
And oxygen, there's two of them, right?
There's one to one.
Oh, times 2. Haha.
There's two.
Oh, there's two.
There's a 2 up there.
96.
So I should have drawn a second one. What was it?
996.
996 in total.
CO, total for those two?
Sure. Carry the 1. I can actually do this.
2640.
Good. The other side.
We'll just get you the total there. 4 times.
1598.
Yeah, 1598 is
Still got
the
it.
first one. Your total is 3434.
34. 34?
Yep.
So you take 2640 minus 3434. That number is going to be negative. And if it's a negative number, it's was it about minus 794?
Yeah.
If it's a negative number, you know it's
Exothermic.
exothermic.